I'd like to thank Professor Hoefler very much for joining the session. I'm very grateful and really looking forward to this talk. Professor Hoefler is a professor of computer science at ETH Zurich, as you can see from the beautiful slide. He's been there since 2013, where he leads the Scalable Parallel Computing Laboratory. He's held visiting positions at Argonne National Labs, Sandia National Labs, Microsoft Research. Professor Hoefler's research aims at understanding the performance of parallel computing systems, ranging from parallel computing architecture through parallel programming to parallel algorithms. So over to you, Torsten.
Thanks, Gaethel. Thanks for having me. This is great, and I actually hope that all of you are enjoying this wonderful event. And it's great that Xilinx is organizing this. Repeatedly, I've heard so many good things from my students about this event. So it's a big honor for me to actually speak to all of you and to briefly interrupt your depth of the tools, let's say. So the idea of this talk is really to give you a higher level picture of what you can do, actually what you can do with those nice tools that you learn if you put a whole lot of stuff around them. And if you try to up-level them. I mean, the idea is to talk about high-performance Python on CPUs, GPUs, which is something you really don't care about. But of course, FPGAs, right? That's the thing here. But for fairness, we have to compare to these different devices. And then also, as Gaethel mentioned, it's not my work, really. It is really the work of a large team that I'm listing many of the people here in my lab. And then this team is led by Tal. Okay, cool. So let's get started right away, and let's motivate this a little bit in case you're not motivated enough why we should be looking at Dataflow style architectures. And in fact, we could argue that what I'm going to tell you now is a Dataflow style programming model, which kind of perfectly fits Dataflow style architectures like FPGAs. So the motivation is going to be pretty generic. As we all know, computing follows a certain trend, and most of you have heard about Moore's law. So here we see the time axis going from 75 until 2015. So 40 years of development in the computing. And here we have a logarithmic scale where the numbers are not too important, but it's logarithmic. So anything that's a line here is actually an exponential growth. So you can see that you have a line that is the up one, the top one, which is Moore's law, which is pretty clear. Everybody knows it. There is another line, the green one, which is the frequency of devices, and kind of the blue one following sequential performance, which kind of follows the frequency. As you know from designs in FPGAs, frequency gives you higher performance. Of course, you can always add a little bit more of resources, but resources are fundamentally limited, while frequency, you have a little bit of a larger range. And then here in around 2006-ish, something seemingly bad happened, because sequential performance and frequency in this plot at least collapse. So what does this mean? Here in this plot, I started going from homogeneous devices to heterogeneous devices, so really to GPUs and accelerated devices, where the frequency is generally lower, the sequential performance is generally lower, but the parallel performance actually follows Moore's law, which means, in other words, Dennard scaling hit. So Dennard scaling really means that we cannot increase the frequency any further without investing significantly more energy. The problem is we could invest more energy, but we don't get the chips cooled. As you can see here with the typical power, it's really realistically, we can cool about 200 watts in a desktop style setting. Otherwise, we need liquid cooling, and it gets relatively complicated, and nobody wants to invest there. In theory, it's all possible, but even data center providers are not running their devices yet in a liquid cooled environment. This will probably come. So really, power is limiting these devices. And what happened is we are going down with the sequential performance in order to get the parallel performance up. We are increasing the number of cores somewhat of an hyper exponential scale here only for a couple of years, because it flattens down pretty quickly. So that is really one of the motivations. The second motivation, and this motivation leads us to more parallelism. The second motivation is that Moore's law is essentially really dead. It is not really following the same trajectory. Some people, like a company with a big blue logo, claims that it's still going, but they often forget that Moore defined a specific constant for the scaling, which is not there anymore. And even TSMC admits that it's slowing down. So basically all the foundries are telling you that it's not really going at the same speed. So what does this really mean? And going back to the past, this whole semiconductor industry followed a pretty impressive trajectory with scaling. And this is where this more than 1 million times performance improvement comes from, by scaling down the feature size of transistors, changing technology a couple of times. Now we are talking about 2 nanometer transistors. I've actually heard 1 nanometer transistors. Obviously, at some point, this is over. You cannot scale this much further because you only have a single layer of atoms, but we are still away from this. So you could actually continue the scaling a little bit. The key insight is in a slightly older process in 45 nanometers, but it's still true relatively seen at smaller processes. It's just that there is no published information there. But the key insight is that you have, for the addition for two 32-bit floating point numbers, you need about 1 picojoule in that process at 0.9 volts. For the multiplication, 3.2 picojoules, but let's just do addition, 1 picojoule. Loading this 1 picojoule from a level 1 cache of 8 kilobyte size, loading the 2 operands for this operation that takes 1 picojoule takes 10 picojoules, so an order of magnitude more in data movement than the addition actually takes. Furthermore, if you're going to larger caches, like 1 megabyte, it's 100 picojoule, another order of magnitude. If we go off chip, we immediately gain another order of magnitude. So 3 orders of magnitude difference between moving the data from DRAM versus processing it. And now the question is, what does this mean? Is this getting worse or better over time? Unfortunately, it's getting worse. So if we were in a room now, I would ask you, who of you knows the Landauer limit? It's a very interesting physical constant. And it has only been really measured in 2012. So it's known for a long time, but it has been measured for only in 2012. And the idea of the Landauer limit is it is the minimal energy needed, like the fundamental energy needed in order to create 1 bit of entropy. So to flip 1 bit. So now you could say, well, if we are living in a physical environment today and we are not in the quantum verse yet, then this is the minimum energy needed in order to perform floating point additions of 32-bit would be 32 times that Landauer limit, which is extremely small. So we are not at the physical constraint yet in terms of computation. However, we are hitting the physical constraints in terms of data movement. If you look at this, as I mentioned, we are shrinking the chip more and more. Unfortunately, the electrical loss in electrical wires, and remember, a chip is a logic layer plus something between 10 and 13 or maybe 15 metal layers on top of it. All the communication, all the data is moved through these metal layers. And this is just normal metal. And the electrical loss in this metal layer is proportional to the resistancy of the material, which is just a constant, times the length of the wire, divided by the cross-section area. So the length is not longer than the chip is, because it has to be in the chip, of course. Divided by the cross-section area is the problem, because of course, if I have smaller and smaller transistors and I need to attach wires to them, my wires have to be smaller and smaller. So the smaller I make the wires, the larger my loss grows. That is bad. This is one of the main reasons for what I'm going to tell you. The data movement is dominating pretty much everything today and is going to continue very soon, because that's just physics. So what does that leave us with? In order to run fast and energy efficient computing devices, we need to worry about the 3 L's. In case you're an American, you will relate to this: spatial locality, temporal locality, and control locality. So it's all about locality, like in the real estate market, at least over in the US. You all know what spatial and temporal locality is. I'm not going to re-explain this. This is something you learn in your early time in school. Control locality is a new, somewhat a new metric that I want to introduce a little bit more. If you care about this kind of thing, you can actually look at this survey, which is pretty well explaining what this is all about. But now let me explain a little bit better what control locality is. And here I want to compare 2 architectures: load store architectures, in brackets CPUs and GPUs, as well as Dataflow architectures, in brackets FPGAs, essentially. Unless we are synthesizing CPU designs into an FPGA, but that would be suboptimal in terms of performance. So a load store architecture, if I wanted to implement X equals A plus B, this architecture contains of a memory, an ALU, registers, a control block, a cache, and data paths and control paths between these devices. I think that's a very basic CPU. How does it now work in practice? Well, in practice, the control logic loads an instruction from main memory that tells it what to execute. Then it configures the data path to execute that instruction. In that case, it was a load. The second instruction is a load, because we need to load both operands. The third instruction is an add. Now the add is actually performed in the ALU, writing it back to a register. And the last instruction is a store back to memory. Some people call this architecture like a tick-tock architecture, because with every tick, I'm loading a control instruction. With every tock, I'm executing some kind of reaction to that instruction. It is not uncommon that the control instruction itself is larger than the operand of the control instruction, right? So this all goes through our data movement bottleneck here. So Now we can look at the energy consumption per executed instruction. That's about 70 picojoule. It's again this ISSC 14 paper, so in the 45 nanometer process. And the actual addition here that happens is this red thing. So it's like 95% overhead in all kinds of cache access, register file access. This is all data movement here, and execution of the control, which is also largely data movement. So now it was already recognized that this may be a kind of a limiting architecture in terms of performance, but here we see the energy consumption. But now let's look at a slightly different architecture, kind of the architectures that we've been talking about, how to synthesize them into these FPGA style devices, or in general, also CGRAs and other Dataflow, static Dataflow devices. So here what we would do in order to implement this operation, we would actually synthesize these adders and the multiplier and buffers to each of those, as well as a data path, like assuming it's a buffered, like it's one cycle per step here. Of course, you could merge multiple in a single cycle if you're clever, blah, 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 but let's just assume this here. And what then happens is that the data is just moved in a very targeted way through these devices, or it's called a data flow architecture. The data flows through these devices essentially in a lockstep manner. And then the energy per operation is suddenly nearly an order of magnitude less, because I have very small memories to address, and the data path is very short if place and route actually succeeds. Well, maybe with the Xilinx tools, you're not always happy or lucky, but usually it's better than in other devices where you can, where you don't specialize your data path to the particular application at hand. So this is what I call control locality here. Here is very low control locality because the control moves between the memory and the execution unit and blah, blah, blah. Here's a very high control locality because the control is distributed to the execution elements. Right? There is no central control unit. Now you can argue that, well, CPUs, vectorized CPUs and GPUs, like the SIMD, single instruction multiple thread architectures, they do something similar to reduce control overhead. With one instruction, they actually execute multiple ALU instructions. Thus, the instruction overhead is much less, of course, if I'm always orchestrating 10 or, I don't know, 64 different operations. Yes, that is very true, but the problem is the register set in these architectures. The problem is that these architectures still have to access very large memories, and you can see the cost here as a reminder, as we had on the earlier slide, which is very different from a laid-out architecture where the registers are personalized to the ALU devices themselves, or to the ALU themselves. Of course, this is much more limited than this. When we are talking about specialization here, it comes at a cost. So somehow these GPUs still have lower control locality, which is why with FPGAs we can achieve a much lower energy consumption per operation, because we lay out the data path specifically to that application at hand. And this is something I want you to keep in mind. That is the only fundamental, or the principal component of the fundamental difference. It's not the only one. There are some hacks there as well, but that's the principal component. So eventually, if I want to do energy efficient or high performance computing, it becomes a data management challenge. That was recognized more than 10 years ago. So I'm not saying anything new. I don't want to claim credit for it. In fact, if you go back to the Department of Energy exascale meetings in 2011, there were slides like this, oh God, hierarchical power costs. And Bill Daly gave a keynote at the Supercomputing 10 conference, communication dominates arithmetic, even in 2010, 12 years ago. And then in 21, my lab was quite late to the game, but we also wanted to focus on transformer networks, which were just invented in 2017 to have a higher impact, where we point out that in machine learning today, essentially it's all about data movement as well. And you may think machine learning is all about matrix multiplying. Yes, but you have to get these matrices into the execution elements, which is very, very expensive if you look at the details. So it is all matrix multiplication, but still the matrix has to flow through your chip. Then there was a very interesting CACM article on the future of microprocessors, also around 10 years ago. I think that was 2015, but I'm not 100% sure. So if you look at this article, which really talks about how microprocessors are going to develop the next 10 years, it's all about data movement again. And this money quote is that basically the future of microprocessors depends on sophisticated software to place computation and data so as to minimize data movement. Okay, let's see how we do this today. Where's our sophisticated software? How do we program these devices today? Well, to a good approximation, today we program devices like we did yesterday, or last year, or maybe 40 years ago, because in fact, nothing changed in the way we program and teach computer science in the last 40 years. So Bacchus' complaint from 1977 is still not solved. because we are living in a world of control-centric programming. We are really worrying about operation costs. When you go to an undergraduate class and learn about operational complexity, you'll learn about operational complexity. You'll learn about the number of operations performed for matrix multiplication, performed for sorting. For sorting, it's the number of comparisons, but nobody tells you about data movement. Like, you're rarely taught about data movement. In fact, I'm teaching a class, but students are typically shocked when they hear about it, because in fact, it is most complex, much more complex than just simple counting operations. So data movement is really implicit. It's mostly ignored unless you start worrying about real performance. Then you suddenly start worrying about it. So we think wrongly about algorithms because we always think about this thing, do this, then that, like a recipe, essentially, but not move the data there and then process it there. Right? Our whole mindset is somewhat wrong. Unfortunately, that's deeply ingrained in the human psyche, I think. It's much easier to reason about algorithms than it is about locations. Right? So that's something on the psychological side. So somehow we have to cross the chasm between algorithms and data-centric computing, because we think algorithmically as humans, but the computer fundamentally is limited by data movement. So we need to translate it into an efficient data movement scheme. So somehow we have to ensure that the domain scientists and the algorithm developers, I'm just saying this in other words again, remain in some control-centric land, because this is how humans think and design algorithms. But the performance engineers, people who get performance out of those codes, they can enter some data-centric land. So some view where you actually look at data computation, or data communication. So, and somehow what we think is that a good intermediate representation could connect the two. Of course, both need to adopt a little bit. Actually, if you want to hear me more ranting about this, we have a YouTube channel where I have a really long rant, on a 12-minute rant on how we think completely wrongly and how to correct this and how to actually have an I/O complexity metric and blah, blah, blah. But I don't have enough time in this talk to go into it, because I want to show you all the cool things that we can do with FPGAs here. So really, to give you a little bit of the overall vision, how this should work in the 21st century for performance portable programming, let me show you the following view graph. So we have a domain scientist. The domain scientist typically thinks at most mathematical equations. Actually, most of the people I'm working with on the climate side, they think in clouds and water and rain and ice and snow, and then they explain all of these things to me, and then I get really confused. Then I'm asking them to write this down as equations, and then I understand a little bit more. But typically, between the domain scientist and the computer scientist is another applied scientist, or like an applied mathematician, that translates all of these things into some kind of other language. In our case, we translate a domain-specific language that the domain scientist can understand, like a NumPy language, or if you're a data domain scientist, then it's PyTorch, TensorFlow. Many of you probably know this, and it's very specific to the problem setting, not to the performance of the problem. Right? It's really not worrying about this. The applied scientist then translates this into some kind of internal representation that we call SDFG, stateful data flow multigraph. So then we have a performance engineer in the game here, which is this little ninja person here. And the idea of the performance engineer is that it's a very capable engineer who can actually work at the details of the code. So this engineer works on this graph that I'm going to explain you in a couple of minutes, and applies transformations to make this graph faster. Furthermore, and at the end, we take the graph after it's being transformed and generate code for different target devices, as I mentioned, CPU, GPU, as well as FPGAs. So one fundamental aspect of this is that the domain scientist lives in happy land, in land that is very easy to program in. So typically tens of lines of code for Python or some high-level language. The performance engineer then is in a more complex environment where we have hundreds of lines of code. And this is usually, hopefully, reusable. That's our goal. So somehow you have a meta program that takes the domain scientist's program and translates that program into a faster representation for execution. And then at the end, we have code generation that just generates code, which is like a compiler backend that can be executed. That's typically thousands of lines of auto-generated code, which you don't want to look at anymore unless you really have to debug it. But then I'm really sorry for you if you have to do it. So the question is now, why Python? I mean, you probably already got the message somehow. If we look at the popularity of languages, you can look at the gradient. So Python is number 2 in June 21, but the gradient is very positive, while number 1 is somewhat negative, even number 3 is negative. So Python will dominate programmer productivity very soon, or is already dominating programmer productivity. So we also support C and C++, by the way, but this talk is all about Python. because Python is the language of computational and data sciences. I mean, that's quite important. And it has a long history of optimizations. So what do I mean by this? There are a lot of different Python frameworks that claim to make Python fast. And in order to compare those in a fair way, we developed a little benchmark that we call NP bench, so NumPy bench, because NumPy, in fact, is the workhorse of Python for scientific computing, for anything that processes large data. So Pandas bases a lot on NumPy. TensorFlow and PyTorch essentially derive from NumPy. All scientific computing frameworks sit on NumPy. So what we do is we took 51 kernels from 9 different domains and arranged them in these different domains and added them to the NumPy benchmark suite. We compare 2 different metrics. One is performance, which is pretty obvious. I mean, yes, we need the fastest thing, but the second one is productivity. So each of these frameworks that I'm going to show you require you to change the Python code a little bit, at least adding another import statement. Right? Some of them require more changes. And this is also what we compare. So these frameworks are just NumPy as NumPy, Pythran, Numba, CuPy, and Dace. So there are more frameworks, but these are the ones that we considered are actually easy to use and kind of production level. So we could now look through all those 51 results. I don't have enough time to do this. I just want to summarize this. And if you look at these different columns here, this is the NumPy baseline. So for the domains, so we have these 9 domains. This is the arithmetic mean or geometric mean. So the yellow column has the arithmetic mean, and the green column says geometric means of speedups. So let me start with the yellow one. This is the NumPy, the time that NumPy takes to process the average time to process this benchmark. Okay, not too important. And this is now the column for speedup of Pythran, Numba, Dace on CPU, Dace on GPU, and CuPy, NVIDIA's CuPy on GPU. So for each of those domains, as well as the total line. And now if you look at those, let us just focus on the Dace thing here, which is the framework I'm talking about, this data-centric framework. You see that it significantly outperforms all the other ones. Right? So it has 13 times on a GPU average speed up, while CuPy is the only other framework that goes to GPUs as 1.6. It's also faster than the recently released, and now I'm blanking, Legion-based framework from, now I'm forgetting the name, from NVIDIA, but bear with me, it'll come back later. And for the CPU case, it has a 10.4x speed up. So now the question is, how do we get this to work? How do we achieve the speed up? And does it work for FPGA and hardware design? And the answer is yes, it will work for FPGA. So just bear with me, and I'm going to explain you exactly how we get there. But I need to fill in a little bit of background on data flow programming first, because that's not generally known. So the idea here is that we have a domain scientist equation, let's say this one, y equals x squared plus sine x divided by pi. And we just wrap this into something that we call a tasklet. We model the input, which is just x, pi is a constant, and we model the output, which is just y. And in fact, we are completely forgetting about the computation, because as I mentioned, computation does not really matter for performance. The data movement matters. So the whole principle is forget about the computation. We call these things memlets. Of course, you cannot totally forget about it, right? You have to generate the valid code to execute it at the end. But for the optimizations, we're only looking at these data movement things that we call memlets. Then if we have an array with data parallelism, of course, you have multiple instances of that array. If you only process one x to one y, then we don't need to talk about it, because it's going to be 2 nanoseconds and then we're done. Usually you process lots of content in an array. So in order to visualize this nicer, this A0 to AN-1, we introduce somehow this notation, which gives us these scopes here. So each of these opening trapezoids has a closing trapezoid and has in the middle a tasklet. And my team likes to call these things a burger because it looks like a hamburger. So that's the meat patty and the ugly bun. So you will see many of these burgers, and just imagine that every single time you see it, it's an iteration space. It goes from 0 to n in that case, and all the iterations internally are independent. Right? That's the definition of a tasklet. A map, and the tasklet is internal. Okay, now you cannot express everything as such maps, so it's easy to see. So we also have multiple states such that you can first process this thing and then this thing. So if you're a compiler engineer, you will see this, what we call a state, could be very close to what you will call a data flow block or a basic block in a compiler intermediate representation. And this would be a state transition edge here. But what we focus on these basic blocks, and in fact, we encourage the programmer to maximize the size of these blocks. This is very, very important. So now talking about the generic concepts, we have data containers. You've seen some of those. We have computations. We have data movement edges, and we have these different syntactical elements here, like the different states and these burger things or maps. You'll see some more of those. I don't have enough time to go into detail, but I will introduce those as they come along such that you can follow. Okay, so what we now do is we are now working at the area of the performance engineer, and we get these stateful data flow multigraphs. By the way, those are all screenshots here. This is real stuff that you can do in our tool. And yeah, this is actually really working, this whole stuff. So this is a pure data flow section. As I mentioned, everything that's in a blue background is pure data flow. There is no control inside this. So everything is triggered by the flow of data, as I mentioned before. So all data movement is explicit. So each arrow defines what data moves. Right, so that's quite important. And then we automatically generate code here. Here in this case, you can already see that's HLS code designed for Xilinx devices. We also generate code for CPU and GPU, but I don't want to spend too much time on the C++ code because, as you probably have seen, it's not the most pretty picture that it draws when you look at it for too long. But what we now do on this graph, we apply transformations to make this graph perform faster. And this is what I want to give you an example for now. Let's say we have this XP operation of X and Y followed by a dot product with W. So two vectors X, Y, dot product with the W, and then we get an output result. We want to move this to an FPGA device. So how do we do this? Well, obviously, we first have to copy these input arrays X, Y, and W somehow to the FPGA. Because we are assuming this is running in some kind of accelerated setting. This is driven by a Python program on the host CPU. The Python program has these things in NumPy, X, Y, and W. And now we grab the underlying C-style array from NumPy and just copy it to the FPGA. This is automatically generated. We now have the internal arrays here, this Z. We now have to map to FPGA memory internally because this may be too large for block RAM. And then the data is copied back to the CPU, of course, at the end. So this is really a fully accelerated code executed from Python. This is all automatically generated code here. I'm just showing you that you see that you're actually saving a lot of time when you do this, because literally this is 3 lines of code in Python. You click a button and it runs on the FPGA. You don't need to write all this boilerplate code stuff. It's pretty obvious that it's easy to generate. So now the problem is if you do this, if you just do this, actually, just going back, and you synthesize with HLS the XP and the dot product code, which of course is still in there, right? So that's not gone. Then it'll run on the FPGA, but it'll run slow as a dog, right? Because as you know, you need to apply all these optimizations to make this fast. And in fact, we do have another tutorial online that we have taught multiple times at Supercomputing and other conferences, how to make these codes, these HLS codes fast, in case you like working with C++, C or C++. But we want to automate that process in our language. So the idea here is that we now, again, have to somehow make sure that this runs fast. So how do we make sure this runs fast? First of all, you want to have separate devices, separate IP blocks for the FPGA to place and route independently. So here we have readers, 2 readers, and these are actually 3 readers, X, Y, and W. So these are all 3 inputs. And then there is an output device as well, output code as well. Furthermore, we want to make sure that between each operator, we are streaming the data in a fine-grained manner, because that's how you program FPGAs. I mean, you know this now after the class. So here we have these streaming connections that basically the output of the dot product, the output of the XP is streamed right into the dot product graph. Right. So this is element by element essentially. And once we implement all these transformations, we get a new generated code, which now looks slightly different. So we now have different tasklets in this code, which is beneficial for the tool because the HLS backend can now place those somewhat independently. They're just connected by interfaces. And in fact, we can do this for both Xilinx Vivado HLS as well as Intel's OpenCL. So we have full portability across the devices. You can see the code is slightly different, but it's still generally the same. Both of these tools are C++ code. You see that you have different pragmas here, pragma IVDEP and pragma HLS. And then you have pragma loop coalesce in the Intel language. But otherwise, and you have this God save us comment here, because if you look at this gets really, really hard. So there are some problems, but not only on the Intel side. So both tools have some interesting issues you have to work around. Okay, so then you can, we could go into details, but I don't have enough time to really go into details. This code is all open source, by the way. And we automatically generate all this boilerplate code that I would hate to write, actually, because it's all this junk that just takes forever to write, and you can build a lot of bugs and then take forever to debug it. And the host device interaction is also fully automatically derived from that representation. Okay, so great. At the end, we have a driver program, which is the Python program that the programmer sees. It's really a normal Python program. Right? You have your input arguments, you declare them as a symbol, you have your NumPy arrays, and then you call the gem function, and the gem function itself will automatically, during runtime, actually runtime compile this thing if it hasn't already done so to the device, run it on the device, start it on the device, copy the thing, execute it on the device, and copy it back. Right, so that's all automatically through this Python API, and then at the end, it's really a normal Python function that you call, and you have to use NumPy arrays. Right, so lists won't work in Python. So with that, we can actually compile all of the Polybench applications. So in fact, we are the first ones who can compile all 30 Polybench applications directly from a NumPy representation. So from Python on Xilinx as well as Intel devices without errors. They actually have correct output. So then to just show you the tooling a little bit, we have a Visual Studio Code integration where you can look at the source code, which is here at the same time as looking at the SDFG itself. And you can see in the animation that you can also apply these transformations. Over here, you see an array of transformations. Like if you want to tile a loop, for example, to optimize that SDFG, you would just select the map here, as you can see, this multiplication map. You can look at the preview, what it would do with the loop tiling. Here we see now 3 different loops that just resulted, and then you can even abort and go back. Right? So you can automatically do all these transformations as a performance engineer with the click of a button. You don't need to write code. You may write code if you want to, but it's much faster because if you just click the button, then the tool will do all these transformations, and you will have less trouble with off-by-one errors and things like I at least like to do every single time I'm applying these transformations. So that's the performance engineer. Another view for the performance engineer is pretty powerful, that you can actually look at the data volume here, as you see when you hover over these objects. You can look at the moved data volume of each of those edges. You can also look at the computational volume, how many flops are executed in each of those blocks. So you can really understand what's going on in your data flow, and that is absolutely necessary in order to build the fastest codes. Furthermore, you can actually debug things, so you can set breakpoints in the Python code, and when you run it, it can show you the generated C code where it breaks. Right, so that is also quite important sometimes, because sometimes the framework is not always 100% correct. This is kind of researchy code, so it's always nicely integrated in all these tools. So really, if you want to play with it, you can actually just download the Visual Studio Code plugin. It's always up to date and downloads pretty much automatically. But now I want to close on what DAYS is, the data-centric parallel Python, and I want to give you a case study how to simulate the weather. In fact, that's a collaboration with Meteo Swiss. That's the Swiss regional weather forecast. As you can see here, the beautiful Alps and some clouds moving, and I'm actually right here right now. So no, I'm actually right here to be precise. So this is Lake Zurich, and here the Bodensee and all of these beautiful lakes. And in fact, CSCS, the Swiss, the Meteo Swiss, with the help of CSCS, of the Swiss National Supercomputing Center, is running all weather forecasting, all production level weather forecasting on GPUs today. In fact, we were the first weather forecasting service worldwide to switch the production to GPU systems with the help of one of my former students who now got a really high-paying job at Google. To make this all happen. So this was a GPU that was in about 2013. So now we're actually looking at, hey, couldn't we take this weather code, this stencil, and because it's such a nice pipelinable code, and somehow shoehorn this on a chip? And then, of course, the first idea, if you want to shoehorn something on a chip, is, hey, let's try this on an FPGA. So you just generate, the idea is you take all these stencils that we can run on the GPU, and we now want to run them as a pipeline, the whole code, or at least large parts of the code. The whole code won't fit on one FPGA, on a circuit, essentially. So let's see how we do this. So really, that's what I just said. And the key is minimize data movement. Like the key is so why do we move away from GPUs? Well, because GPUs have this tick-tock architecture. They still have to go through these large memories. And we had this hypothesis that if we orchestrate the data movement directly, we would be much more efficient. We will see how that worked out. It worked out reasonably, I would say. There's still some problems. And at the end, the idea is to really compile from a high-level scientific domain-specific language right to a circuit which can be synthesized on an FPGA. So let's get a little bit more into details of what a stencil operation is in weather and climate forecast. That is the basic primitive that's performed. So the Earth is discretized into a 2D grid of cells. So here in this case, n times m many cells. Right? So these are your points that hold some kind of value. Typically what you do, or what you have in weather and climate simulations, is each of those cells somewhat interacts with its neighbors. It's pretty likely that if there is sun 1 kilometer from me north, then I have also sun. Right? So that's kind of the interaction. But of course, there may be a gradient of humidity. And if the gradient gets too large, at some point it becomes a cloud. And then I have less sun. Right? So that's pretty obvious that in weather and climate simulations, there are local interactions. And this is represented by these stencil-like shapes where you update the middle point with the values of its neighbors. And you do this over and over and over again, and that's what you call a weather simulation at the end. So now a real weather simulation actually does not only have a single stencil like that guy, but in fact has hundreds of these stencils. And these stencils, they produce so-called fields. So a stencil program, in brackets, a weather simulation or climate simulation for that purpose, is a directed acyclic graph of those stencil operations that are working on the same grid, because it's always the Earth, right? So the grid doesn't change. But the operation changes because you may be interested in humidity. This may be a humidity stencil. This may be a temperature stencil. There may be a pollen stencil because pollen, the pollen flow depends on humidity as well as the temperature, and blah, blah, blah. You can now define arbitrarily long, complex stencil chains. And in fact, this is done in practice. So what we did is we designed the Stencil Framework under the lead of Johannes Stefan Licht, who is one of my students who just graduated and found a job recently. So unfortunately, he's off the market. So the idea here was that we have a JSON-based front end where the climate scientist defines all of those stencils. And I will get a little bit more into detail now on this, because this is actually your climate program. And in fact, many people are working on simplifying writing these climate programs for climate scientists. So one of the tools being developed there is called Grid Tools, that is developed at CSCS in collaboration with many weather centers like Meteo Swiss, ECMWF, and many others that are interested in the outcome. So we are using one of those DSLs essentially. But that's not what I want to talk about, because we are not climate scientists. I couldn't even explain exactly how it works. I can explain how it works in the hardware mapping. How do we map this thing to the hardware? The idea here is that we have these many stencils, and we buffer these stencils in internal buffers to maximize data reuse. And that is quite cool about these Dataflow architectures, because a GPU will read the inputs for these stencils from main memory and write it back to main memory. And we have to rely on either orchestrated scratchpad in terms of shared memory, or in the CPU case in terms of automatic caching. On an FPGA, I can actually lay out, or in a circuit, I can lay out these fixed stencils in a way that I can exploit all available reuse, that by design, every memory relocation is read exactly once. Right? So this is the wonderful thing about circuits. There is no non-determinism. There's exactly, I determine how often it's read. On a CPU, if you've done performance optimization, you realize that this is usually a pain to figure out what the cache is doing, and it usually fools you because it's super advanced, or at least it thinks it's super advanced. So this is a big benefit of hardware design. So the idea here is that we have this 2D grid, X or M by N it was, and we are moving through this grid, as you can see, in that order, and every single point is computed from the neighboring points. So all the white area is now already computed. The gray area is what we cache in the FPGA BRAM, essentially, or in the pipeline. It depends on whether that's BRAM or actually registers. And so this is typically 2 lines, as you can see here. So if this is the M dimension, we have 2M plus 1 many elements here. And then the remaining thing is just streamed. So at the end, we're just moving in a nice way through this array. And we only need to store 2 rows plus 1 element in the internal memory. Okay, so that's quite important. If we cannot store 2 rows, we're a little bit into trouble, but typically we can. And I can talk about this in the Q&A session if you really care. For 3-dimensional stencils, we would need to store full slices. So in general, for n-dimensional stencils, you would need to store n-1 dimensional hyperplanes, 2 of those n-1 dimensional hyperplanes. Okay, but with this, if this works, then we can prove that every stencil operation reads memory only once. And this is what we show for all of the examples that I'm showing later. So furthermore, we can have global reuse. If you have the stencil A, B, and C, it may be that both of those stencils actually read the same input element, the same input field, because, I don't know, that may be humidity, and both of those need humidity for their calculation. Furthermore, stencil A may produce a value that is read by both B and C. So there's 2 types of reuse. One is from main memory, and the other one is from the pipeline that is computing on the device. So the one from main memory is relatively simple because you just orchestrate the memory like you want to have buffering in here. The problem happens if you have a producer and 2 consumers of the same item. And that's the problem here. And if you're a hardware designer, that's not a problem for you because you know what delay buffers are. But if you're new to hardware design, then let me explain this in 5 minutes here. The idea is I have this producer that writes A of 0. And we have intermediate buffers, right? So let me just show the buffers. So we have a stencil B that consumes 2 elements and produces 1 element. And we have a stencil C that consumes 2 elements and also produces 1 element, but it doesn't matter. So now let's say we produce A0 here. A0 goes immediately into those 2 pipes because it needs to be consumed by both B and C. Right? So it goes in here and in here. And now I'm producing A1 as the next pipeline stage. My problem is now this pipeline cannot move because that pipeline needs the second input, while this pipeline is full, so it cannot accept the second input. So now I have a deadlock dependency because the path is essentially full. Well, the way to fix it is super simple for hardware designers. We introduce a so-called delay buffer. So basically here, we buffer that A1 either on the line or close to the output, such that we can fulfill and store these 2 copies at the same time, right? So this is something that's very simple, but actually you need to have it, otherwise your design will just not work. So our tool is automatically deriving those delay buffers for you, so it doesn't really need to worry about this, but this is like one of the major technical challenges we had to address to make this work. And because we needed to look at the path delay, and now imagine not just a simple example, now imagine a stencil program with a couple of dozens of stencils that are connected in weird ways. And also the pipeline depth of each stencil and whatnot. So it gets quite complex in the details. And if you want to understand this in detail, I recommend you read the Stencilflow paper. It's all documented well there. The paper is cited down here. Okay, so now we have translated all of this into the stateful data flow multigraph, as I mentioned before. And I don't need to re-explain this all. This is the thing that generates FPGA code at the end. We have these pure data flow states. Somehow we make sure that we have these disjoint sections, because each of those disjoint sections, they are connected by these dotted things here, or oval with a dotted line. And these are streams. So, and they match by name, like this read A to B0 is hopefully consumed somewhere. Hey, read A to B0. Right? Because we didn't draw all the lines and it would get too messy. But these are separate processing elements on the device, separate circuits that are connected through these so-called pipes. Okay, that's very important for the place and route, because otherwise place and route doesn't work, as I mentioned. You want very small elements, many very small elements. Then we have library nodes in here, which are doing the actual calculation. So these define what the stencil actually does. As I mentioned, we don't really care about those for the optimization, but we do, of course, care about those for the execution of the code, because they need to execute the right calculation. And they are later actually expanded to the correct implementation. In this example, we are choosing Intel FPGAs, but the same is true for Xilinx FPGAs. we're choosing Intel mainly because at that time we didn't have the XACC cluster, so we were not that lucky and had to rely on an Intel cluster. So we will now generate these expansions here. Oops, no, I did something. No, somehow my PowerPoint's, okay, so we generate these expansions, and this is super mega slow suddenly. And we could look at this graph in detail, but this is just one particular stencil, so let's not spend too much time on this. And at the end, we are generating these loops, these fully pipelined loops. That's just all of this Pragma HLS stuff that I showed you before. We use architectural specific shift registers, which is this God save me thing that we had before. And then we have this automatically generated code that's generated by the back end that we don't need to look at, but I just want to show you that you believe this is all legit. Okay, so looking at performance. So we have this Bitware 520N. It's a Stratix 10 device. It has 4 Ethernet ports with 4DG each. And with a single node performance, as we ramp up the pipeline, so we are using more and more resources here until we fill essentially the whole chip. That's the performance we get for one chip. But we can use the streaming messaging interface that we developed to go multi-chip or multi-node in this case. And with 2 FPGAs, we essentially double, and then with 4, and then with 8, and it scales nicely. So that's also supported multi-FPGA, at least for these Bitware boards, multi-FPGA implementations. So looking at the performance is pretty nice because for at least the diffusion 2D and the diffusion 3D, we have a vector width of 8 here. We can compare to a manually tuned example that is implementing exactly the same stencil. And we beat the manually tuned example here. This is written in OpenCL. By Zuhuri et al., a very, very competent researcher, by the way. But the OpenCL framework is limiting the performance of this thing here. As you can see, the resource utilization is actually higher. So we only have 51%, 68% of the DSPs. Here it's 86 and 80. However, our frequency is higher, so we beat them on frequency. Because we generate these very small units, what OpenCL doesn't quite allow. At the end, this is run as a Python program as just normal. Now, to show a little bit more complex example, we can have a full horizontal diffusion program that is from the weather front end of our partners that is much more complicated. So it's a long DSL that's a real thing that is actually really used in a real code. So here we have all these fields, 1D fields, 3D fields, outputs, and all these stencils. I don't want to explain this in detail. This is one of the more complex codes here. It performs 130 operations per grid point and has lots of data-dependent branches and a very low arithmetic intensity. So at the end on the Stratix 10, we get this performance of 145 gigaops per second, which is great. If we compare it to a Xeon, a 12-core Xeon, then we're like, wow, we win big time. This is great and wonderful. Unfortunately, if we compare it to a GPU, we lose big time, as you can see. Even with a P100, which is a quite old GPU that beats us, and the V100, which is a more modern, not even the latest one. I mean, this paper is a year old. Not even the latest one is beating us big time. Why? Well, because we are memory bandwidth limited. And until a couple of months ago, or maybe a year ago, that was the major Achilles heel of FPGAs, the bandwidth limitation, because we didn't have high bandwidth memory. These GPUs had a factor of 10 more. Of course, they achieve a much higher performance in a memory bound application. That's just clear because we couldn't read all the data. The experiment we ran was just saying, okay, let's just fake the data. Let's just assume we have infinite memory bandwidth, and we just produce random data at the inlet. And then we get 500 gigaops per second, which is now faster than the P100. And by the way, they're in about the same silicon process and slightly slower only than the V100, which is a more advanced silicon process. So now we could conclude if FPGA vendors would get their act together and build fast memories, which Xilinx did, because we have these HBM FPGAs today, then we should probably be able to beat GPUs with those devices. And then it becomes only a cost argument, how to program them and and whether we want to purchase large clusters with these. Actually, by the way, we get about 380 megahertz at a 50% DSP utilization here. So it's not the latest, greatest. I mean, Intel is quoting something like 800 megahertz max, but these are all imaginary numbers. I think I've never seen those. And it's not just Intel who's claiming these imaginary numbers sometimes. Okay, so really the major conclusion is that the Stratix 10 is held back by insufficient bandwidth, which is fixed now in the more modern devices. So that's quite nice. So now we have actually a chance of doing really cool stuff. And we didn't get to it because, as I mentioned, the lead of this of this effort is now in industry. But you can download all the code and run it yourself. So it's fully available, reproduced, and whatnot. So please break it and work with it if you want. So now the holy grail for us, or for my team, is somehow, can we get a full weather code maybe on an FPGA? Right. So there is actually a quite substantial effort going on in Europe, which Switzerland was just removed off the European Union recently, about the somehow creating a digital twin of the whole Earth. And there is this very nice position paper about the digital revolution of Earth system science, where we outline what would it take to build a real-time digital twin of planet Earth. For that design, we used a GPU-based design because at the time it seemed the most realistic design given the A100 results. I mean, what we could actually buy and, V100 results, what we could actually buy and execute. And you can see in this paper that we would require a reasonably large cluster to actually build this digital twin and then really understand the anthropomorphic impact of basically humanity on the Earth and simulate the future. So just to close out the talk, just cycling back to the beginning, the data-centric parallel programming framework. So it takes, as a versatile platform, it takes multiple different input languages. Like NumPy, we have a Fortran version that is nearly done now. We are actually going to run the full weather code through the Fortran version, hopefully very soon, hopefully this week, actually. And then it outputs code for NVIDIA GPU, all kinds of GPUs, all kinds of CPUs, including ARM SVE, as well as RTL and Xilinx and Intel FPGAs. And it's relatively easy to extend to your own coprocessor or processor. So we're working with a set of people working on RISC-V and on various backends and machine learning accelerators. By the way, we also have a machine learning input, so we can take PyTorch codes basically as is as well. So to just show you that this thing also scales, I showed you very small scale results with up to 4 nodes, but in fact, DACE is built for extreme scale. So in 2019, we ran it on the largest supercomputer on the planet, which at the time was Oak Ridge Summit machine with, I believe, something like 20,000 GPUs, but I'm not fully sure, but in the tens of thousands of GPUs, V100 GPUs. And we won the prestigious Gordon Bell Prize with the DACE implementation. At that time, it wasn't fully done, so there was a lot of manual management in addition to DACE, but we really managed to execute it on a full scale, the largest supercomputer. So it scales from the smallest FPGA to on the pink board, essentially, down up to the largest machine on the planet. So just to wrap up my talk, what I tried to make the point is that high performance computing and low energy computing is a data management challenge. It's all about data. It's all about data movement. Furthermore, there is an idea how to move forward from the domain scientist's perspective through a performance engineering effort with transformations on an internal representation to automated code generation to conquer these things. Because forget it, I mean, no climate scientist will write in Vivado HLS, that I tell you. They will not touch it with a stick. Even not with a very long stick, because it is too complex. They will not even touch C++. They will want to stick to their very nice environment, which is either Fortran or more recently Python. Then we looked at this NP bench as a sideline. So if you wanted to develop a Python high performance implementation, you should look at NP bench as a fair benchmark to compare the various ones. Then I showed you how to generate hardware descriptions through Vivado HLS tools. I showed you a particular example of Stencil Flow to a real climate and weather application, and then some results for a realistic weather stencil. And if you enjoyed that talk, we have a YouTube channel with many more related talks, also going much more in depth on the FPGA side, as there's a tutorial I mentioned, but there are also many other talks that I couldn't give talking about similar aspects. So with that, thank you very much, and I am happy to take any questions.